This is our home reference time clock, so essentially the most accurate clock that we have at home. It does synchronize the time with official atomic clock and receives time signal from two sources. One source is time signal National Physical Laboratory in UK in Ainthorne, so-called MSF 60 signal, and the other is GPS time from GPS satellites. As you can see, the display is built around LED matrix. Each character has 7 dots high, and 5 dots width. Height of each character is 7 centimeters, and the distance between each dot is 1 centimeter. So there are 7 rows here that are used to display information on this in this clock. Additionally, there are 2 LEDs here. I'll make them a little bit brighter. One blue and one green that show the signal being received. So blue is GPS signal, green is a radio signal being received by the clock. And then we have controls here at the bottom, just below the display. There are 2 encoders. Left one, the most left one, is the brightness. By pushing the encoder, we can switch between the manual mode and automatic mode. So right now it is full brightness. If I rotate it all the way to the, or if I rotate it to the left, I'm going to dim the brightness. And that's the least brightness. I'm not sure you can even see this right now on camera. And then there is automatic mode. If I push it here, then it should adjust to the brightness in the room. It updates every 30 seconds, so it reads. There is a light sensor here, just above this digit, and every 30 seconds it checks for the brightness and then adjusts the brightness depending on the brightness in the room. So if I simulate that there is a complete dark here, it goes into the dim setting. If I remove my finger and simulate there is a little bit more light, or simulate, well, there's a little bit more light coming to the sensor, it should within 30 seconds increase the brightness. Here we go. Then there is a color change. So this knob here allows us to change the color and to select the display color. Then there is a push button that changes the mode. So right now we can see time. When I push it, it shows the date, and then it goes back to the time. So every time we push the button, we can see the date. And the one to the right, here the knob to the right is potentiometer that allows to dim this signal reception LEDs. All the way to the right, you can see that these LEDs are very bright. Here, the signal reception. If I turn it all the way to the left, the green one is not visible, the blue one is barely visible. The reason for that is that the blue LED is a super bright LED, and using the same potentiometer to regulate current through both LEDs, it's not enough. The dimming or the amount of current that is limited, it's not enough to completely bring it down, the brightness. But the green LED is a more conventional LED with a sort of like regular brightness. So that shows the difference between the super bright LED and the normal LED. So this is how the clock looks from behind, from the hardware side. Actually it is built around two boards. So the display is on the top board and all electronics is on the board that is attached to the front. So the controls and the display is in the front, and all electronics is for the ease of servicing. It is attached to the board that here on these screws is fixed to the front board. Now what we've got here is two Arduino Unos. So this is number one and this is number two. Number one is responsible for displaying the controlling the LED matrix, so displaying the information, displaying the time on the LED matrix. Is responsible for controlling or taking information from all the knobs, or from encoders and the switch to be precise. It also takes the information of I2C line from the light sensor that sits here, and takes the time from the real-time controller, real-time module that is here in between Arduinos. Here you can see connector for the lines that go to the display. Here are encoders and the switch and RTC module. And the Arduino number 2 is communicating with the Arduino number 1 and the real-time controller over I2C line. So that's why RTC is sitting in between, because Arduino number 2 is essentially receiving all the data from the GPS module that sits here, and from the and radio time signal that comes through this board, through the 2 transistor voltage converter, and I showed in the other video how it works. And this signal from radio signal and GPS signal goes into the digital pins of the Arduino number 2, and then the Arduino processes this signal, this raw signal, into the time that then is put into the RTC. So RTC receives the time from the Arduino number 2, and Arduino number 1 takes time from the RTC and displays this on the LED matrix. And another thing is 5 amps, 5 volts power supply that drives and that provides power to the LED. That's 5 amps is probably the maximum current that these LEDs are going to take. It's most likely, and most of the time, it is less. This is basically for in case all LEDs would light at the maximum intensity at the same time. That would be probably about 5 amps. But it is much less during normal run. And then we can see quite a big capacitor here on the DC line, just to smooth the power supply for all the circuitry in case the brightness changes quite rapidly to prevent any voltage drops. And another thing that we can see here is the GPS antenna. It is mounted on the magnetic kind of support, so I can adjust this freely all the way around. And then there is a mains power, and something that is probably not very clearly visible here is a connector or radio time signal is separate, and it needs to be separate because there's too much electrical noise around this circuitry here, and basically the MSF signal is not possible to receive it in the proximity of this PSU and Arduinos, and that's why it's on the cable and outside of it. The cable is around 3 meters long, and this is the antenna in the separate enclosure. So you can see a ferrite antenna here, and the receiver module actually sits inside this capsule, and down this cable there is basically power supply, 3.3 volts power supply for the board, and the data pulses are going down to this circuit here. You can see it's quite sensitive. There is a green control LED that would light normally if the signal was received. The fact that I'm already holding it in hand close to the circuit already sort of like disturb it, and there is no signal received. And essentially this is all the hardware. Let's explain the hardware arrangement behind the clock. So there are two Arduinos. So this is Arduino Uno number 1, and the connections to this Arduino are as follows. There is a light sensor. Sorry, change the pen. There is a light sensor. The symbol is GY302, and this is I2C, 5-volt sensor. So basically the connections are SDA, SCL, so A5 and A4, plus 5 volts and ground. Then the next thing connected to number 1 Arduino is the display. So there are 7 LED strips, and each strip is part of WS2812B strip, and this is 96 LEDs per meter. So the distance between each dot is 1 centimeter LED to LED distance. Okay, and that and the output from the Arduino are connected to the resistors. There is 470 ohm resistor, and that goes to D10 to D4 outputs. Okay, so that's the display. Then we have encoders and a switch. So we have two encoders, and the outputs from encoders are connected to D3, D2 and D10, and then the other encoder is connected to A1 and A0 in the digital mode, and obviously both of them need 5 volts and ground, and 5 volts and ground. I didn't mention that the LED strips are connected directly to PSU 5 volts ground. Okay, and then we have one switch, that is connected to D12 and ground. And then finally, final component is connected, module that is connected to Arduino Uno number 1 is real-time clock, and this is again I2C. This is connected obviously to SDA, SCL, 5 volts and ground. And these are connections for Arduino Uno number 1. The Arduino Uno number 2 are connected to real-time clock. What I'm going to do, I'm going to put like a little bracket here, and Arduino Uno number 2, there is another bracket here. So the real-time clock is connected on, or I2C line is basically connecting Arduino Uno number 1, real-time clock, Arduino Uno number 2, and also light sensor is on the same I2C line. I hope it makes a little bit of a sense. And then Arduino Uno number 2 has GPS module, and the GPS module we use here in this project is GY Neo 6M, and then obviously it needs is a transmission line, receiving line, 5 volts and ground. So that's GPS module, and that goes to I think D3 and D4, if I remember correctly. So transmission and receiving pins on the GPS module are connected to D3, D4, if I'm not connected, or D2, D3. I don't remember right now from the top of my head where exactly was it connected. And then we have radio signal, radio time signal receiver, and that is the symbol of the of this is WWVB, and that's the 60 kilohertz module, because for German time signal you need, for DCF you need 77 kilohertz. We need 60 kilohertz, so it is actually MSF signal receiver on the 60 kilohertz from Athorn, and this is based on the CME 6005 integrated circuit. I'm not sure whether this module can work out of 5 volts. The specifications that I received together with this module were talking about maximum voltage 3.5 volts. That's why we converted this voltage supply to 3.3 volts. There is ground, and obviously it is connected to D2 or D4. It's between GPS modules. They use D2, D3, D4 input, output on the Arduino number 2. So Arduino number 2 is mainly responsible for getting the time, converting this to the, getting the signal from the GPS from the MSF radio time signal receiver, converting these signals into the current time and date, and then putting this information into real-time controller. Arduino 1 is responsible for displaying the information on the LED matrix, is responsible for controlling the matrix by the light sensors and the encoders that give us the brightness and the color, and that's essentially how the hardware is arranged. And on top of that, we have switching power supply that provides 5 volts and 5 amps. The PSU has on the output and 5 volts output. There is also capacitor, 1000 microfarads, just to provide a slightly better stability of the voltage. In case there is a surge of demand, especially this LED matrix can make a difference. I hope it makes sense from the hardware point of view. There is nothing complicated here.
The Arduino program uses the following libraries: using software serial for interrupt connection and GPS to decode the signal from the GPS module. This is the RTC module used to keep up the time when there's no signal. These are the following variables used later in the program, with timers to adjust certain features of the clock. We define an interrupt pin used for the radio signal and initialize all our modules. In the main loop, we only have the GPS signal used to decode the data. The interrupt pin handles the radio signal and does not need to be included in the main loop. This is the function used to calculate the MSF signal time. The signal is calculated by reading pulses via the interrupt pin and measuring it with built-in Arduino timer.
I wouldn't go into details. If someone is interested, they can find out details in the code itself.
This function uses the weighted tables found on the NPL Technical Info website to calculate the time and date. It includes parity bits to detect the validity of the hour, minute, week, month, and year separately. And each signal is only the time is only updated if all the parity bits match up
That's the biggest problem, that the signal is quite noisy and we have to reject errors from the valid pulses.
This function reads the length of each pulse and then updates the bits, which are then used to decode the symbol later, the radio signal later. This function reads the length of each pulse and then assigns it to a 2-bit value based on the NPL specifications.